Hello, my name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. Taught here a couple decades at Elizabethtown College, taught at Purdue University. Before that, I've also taught at University of Trento in Italy, University of Delaware, and San Francisco State University. IBM Research and robotics hospital before that. And in the 1980s, built high-tech office parks for computer companies and other people in Texas and California. So this is an introductory lecture, and I'm going to share screen. We are in this intro course, Computer Architecture and High-Tech Fundamentals, and this is the course outline. And we're down here around 18 and 19, and I'm going to do both of those one after the other. They're available in PDF here on the web server at the college, as well as PPTX with embedded audio, and I've saved those as MP4s and uploaded them to YouTube. So go to YouTube. Open another window here. There's playlists. I haven't labeled a number on the playlist for the course. This is intro high-tech lectures. So we're in here and we're down in here. So I'm going to play this one, and then tell a little story and interject at times as needed, with some discussion after the two.
Complex instruction set computing versus RISC, reduced instruction set computing, and also the difference between assembly language and higher level languages. Firstly here, this is more of a footnote for this class, the accumulator architecture. You know from this course, and perhaps other people listening from other courses should know, or other courses with me should know, that the registers in the computer are fast static RAM, very close to the CPU cores or multiprocessors on the same piece of silicon. And those registers nowadays don't necessarily have a default register that catches all the calculations coming out of the arithmetic logic unit, the ALU. In olden days, and still in some microcontrollers, you have an accumulator, which is a default register that the results of calculations go into. Now here's a history in this table of not such ancient history. There's a number of very recent machines here, are relatively recent. I guess they're all older now, but some of them are still very relevant. So you see 1949s and 1950s and 60s. Now those are definitely old machines. The IBM 360s in 1964. Well, those were still around in the early 80s. I actually built, I managed the development for the development of $100 million worth of high-tech real estate development, office parks in Texas and California, and put a couple IBM 360 raised floor computer rooms in. And then also the CDC, that third one there, Controlled Data Corporation. I met with them in San Diego and almost helped build a building for them. DEC, those that went kind of out of business. Dr. Tom Leap, my colleague, is a fan of those. He had one around that I believe he sold just for the gold in it. Had $1,400 worth of gold and gave it to the computer science club. Then you see, 1972s and the Intel 8008, so the very first single chip kind of microprocessor processors, and the Motorola 6800. I had an HP calculator, had a whole estimating business based on that. And then that became the 68,000 later on. You see a couple slots down there. That was in all the original Apples until they went to the recent Intel processors now. So they used to have that Motorola processor in there. Also, ARM now, you see that's in quite a few places now, cell phones, and that's becoming the most prolific of processors and microcontrollers now too. MIPS, I could say things about that in HP. About Spark, these were in Sun workstations, some of the very first things in the late 80s, early 90s, Unix-based systems in the research labs I worked in. Those were powerful machines, some of the very first multiprocessor machines, workstation class machines. Power PC chip, I told you a story about that in another class. The development of the Power PC chip up in Burlington, Vermont. I almost went up and worked on that when I was at IBM. And that whole story of that is to help Motorola and Apple, which seems odd, since the IBM PC was considered, the dominant computing PC in the 80s that Apple was competing against. However, the Wintel machine now, which Windows and Intel, is a vast marketplace with many people in it. And IBM, when I was in there, I told that story. Richard Attardi, I remember, I had a 2-hour interview with him when I got in there. He had a PhD, and he was the head of the microelectronics division with 75,000 employees. So I thought I'd, ask him some questions. I asked him how he could lose out on the PC market. And he said, look, we never valued that more than 10% of our profits. We make most of our money on the larger systems and services, hardware and software, things that I actually worked on at IBM after that. And the Power PC chip was just an attempt to help keep the market keep a free marketplace. It was developed to help Motorola and Apple, because before then, you had, with a Motorola processor inside of an Apple, you had to run an emulation of the Intel instruction set to run any kind of applications developed for Windows. And so this was an attempt, a successful attempt to overcome that. It was some of the very first 32-bit processing, and all, which seems like not much to talk about now, but we did 64-bit processing on large machines right around, but for the PCs, and it's still in gaming systems. It's a very good chip. And then here's DAC and HP again. HP has always been a very high quality company, not maybe as high quality as they used to be. And then AMD, we've talked about that already. That's essentially a competitor to Intel, however, works with the same instruction set developed by Intel. So that's a little bit of history there. This slide talks about compact code and stack architectures. My HP 41C had a stack that's the way it worked. And you would load things in to the stack, you push them in and pop them off, and you'd set up your equations and your calculations. Actually, less keystrokes in your algorithm or your calculations for engineering calculations to do that. It's not prevalent now in any kind of machines that might interest you, so we'll move on. Now, it's not spelled out here specifically. They refer to these high-level language computing architectures. Traditionally, it's CISC, C-I-S-C, for complex instruction set computing, versus RISC, reduced instruction set computing. So I'm going to say that and refer to it that way. Now, complex instruction set computing has many more instructions, fancy addressing modes for where the operand data is and all the instructions. I won't get into the details of all that. You can take other advanced courses with me to discuss that. Reduced instruction set computing came about, several decades ago. Actually, long time ago. I remember when it was, but it was based on the idea that most programmers, most compilers and operating systems the compilers didn't make use of the complex instructions. And so there was overhead involved in that. And so it just reduced the number of instructions and just left the ones more likely to be used. However, there were other things that went along with that. And in more advanced classes, we'll talk about that. There's a thing called an instruction format, where you lay out the opcode that tells what the instruction does. This is machine language, which is a direct one-to-one correlation to assembly language. And then there's operand fields, which determine what the data is, if it's embedded right in the instruction, or where to get it. And there's a variety of places you could get it. We won't discuss here. Now those fields were variable depending on the instruction. The actual length of the whole instruction was variable too. It's faster to have a fixed fields in your instructions for execution, for decoding. The machine can begin to immediately go fetch operand as soon as it sees the opcode and knows right where the opcode is going to be. It's a fixed set of bits. In IBM, we had a big complex machine with a complex instruction set. So we had actually some bits that say, go get the rest of the opcode somewhere else. It was that big because we got up to 1,400 instructions when I was there. Typical Pentium families with the Katami extensions around order of magnitude 600-700. Microcontrollers are around, started at 100 up to 200-300. Simple microcontrollers like a PIC or 32. You can't do much with anything less than that. But anyway, so there are other things that came along with RISC other than just reducing the number of instructions. It would certainly be just a little essay kind of question if I ever asked you here, but it probably is more detailed than I want you to know for this particular course. There are other things that happen, the hardware control versus, or the hardwired control unit in the CPU versus a programmed in nanocode. Don't want to get into that in this course. The control unit that controls the data flow, or the finite state machine we discussed in 332 class, the digital design 1 class, we designed that is hardwired instead of microprogrammed in the RISC. Also, you have more registers in the RISC instruction set, and you make use of them with a simpler instruction. So RISC, RISC comes along with a number of things other than just reducing the number of instructions. And then we're not going to talk about the history of ARM. This is a brief history of the x86 Intel microprocessors. We will we'll visit this again in another way later on. However, for now, we did already have a historical look at developments over time, and I did tell you the story of the PowerPC development and how that was an IBM thing to compete, help the market, keep the marketplace alive, because Motorola and Apple just couldn't afford to compete against the Wintel machines. So, that story I think is a little more valuable. I could talk here if anybody was interested, but I'm not going to take the time now about the development of each of these things over time with 286, 386, 46 and the Pentiums and what changed in the instructions and all the details. I used to teach about all that. It's not quite so relevant recently. And then the Motorola 68000 series that competed with that, it was actually a very elegant instruction set. So and assembly language went with that. So the first thing that I learned before I ever went to IBM research, before I finished my master's degree, before I got my PhD and went to Purdue. And Purdue, we used Intel. I almost switched to the Motorola when I came to E-Town 21 years ago, just because of its elegance and its quality of its textbooks. And they had a college in Schaumburg, Illinois. They called it a college. It was a training center, but it was super high quality. Okay, so no more on history, well, of hardware. This is a brief history of programming languages. I'm not going to go into all the details here. The first thing I ever programmed was in 1982, I think it was, Fortran. on cards. We would punch cards, and you have a stack of cards and walk up with your stack of cards and hand it to somebody, a deck of cards that you punched. Each card was one line of code. You punch each line of code onto a card, and then you'd hand the stack to somebody who would then run it. Sometimes you have to wait in line, and then you get a printout, and then you get syntax error on one line. You go back and retype the card, wait in line, hand the stack again. It was ridiculously long. But that's how it all started. Nobody had their own computer back then. Of course, things changed quite a bit, and that's ancient history. And they talk about different languages here. You can look at the whole development. COBOL, that's a business. There's still machines that run COBOL. Some first programming languages, E-Town. I've been here 21 years, and before that, 10 years before that, there was a COBOL. And then other languages. The next slide. C and Unix. That was when that all came out of AT&T Bell Labs research when AT&T was a monopoly until they broke up into all the baby bells. When the monopoly won advantage of the monopoly, if they're good about their dominance, they do put a lot of money into research. So, Bell Labs, that was the top of research, and that came out of Bell Labs. And then, later object-oriented programming languages, C++ and Java, which you learn now. Engineers still need to learn, and operating systems people certainly, systems level programming is not object-oriented. There's some overhead with doing that. It was powerful. Most application stuff now is written that way. There's still though things, military things, aerospace things that are written in C. Talk to people there, and they confirm that. On a brief history of compilers. Now, I did mention, so a compiler, you take high-level language and you compile it down into, gets down into machine code. Now at IBM, we also would, at the same time, we wrote in PLX, which was like a mixture of Fortran and then looked a little bit like Pascal and like the case statements and things like that. But it was a high-level language, and then we would drop into assembler at times. But we could get the compiler to actually spit out assembler equivalent, even though we didn't write, even for the stuff we didn't write in assembler. And then we could compare the speed. It was a parallel processing compiler. We could compare how efficient the compiler was to what we could do by writing our own assembly language, the one-to-one mapping to machine language. And we played beat the compiler, not just for fun, but to save nanoseconds, billionths of a second of execution on things that run over and over, a billion times, many billions of times, it adds up. So, and that's the kind of stuff we were doing, testing machines and what they do in general. So I did mention that I wanted you to know about the difference between assembly language and high-level language. And I didn't type it out here. There's going to be a slide presentation coming up the next lecture where you'll see that. So you're saying, where does it say that exactly in here? Well, it's in here in this section, just talking about it, because when you compile, you get down to machine code. And machine code is a one-to-one mapping to assembly language. And so if you write an assembly language, it's no less machine instructions. There's one machine instruction for each line of assembly language. That's the intent of assembly language. And you learn that with me in engineering CS 333. This is another course before that, other than the one you're in listening to this right now. In 230, which is an introductory class, then you learn assembly language. So 333 is Digital Design 2, and you haven't had that yet, and that's not this course. You haven't had one yet. That's not this course. And then 333 is Digital Design 2, assembly language, right? And interfacing. And the reason they're together like that is because you're down at the machine level. You learn about this advanced circuits that implement things, machine language in more detail. Then you learn at 332, which is Design 1. You learn assembly language, syntax, and simulation, and boards, development boards, and interfacing, which is, in my opinion, and most people's opinion, done best at the machine level. You're talking to the ports directly, you understand exactly what's going on with the machine. So you can interface it with other machines. And further reading, you can do that on your own. Okay.
So I didn't mention in the beginning here of this presentation, because it's part of the course, that course context here. So in computer engineering, robotics, and syllabi. And then this course syllabus. And this course, by the way, is an introductory course which was required for more than 2 decades at Elizabethtown College. And we're restructuring now and doing things a little bit differently. So this will now be an elective course, which means I have to make sure people in advanced courses get some of this content somehow in those courses too. So we're in here, but this is all part of the restructuring. Up here, you can see how I was mentioning 333 and 332. That's getting restructured into one course with a lab, intensely combining, because it's really going to pack in there pretty tight. I need to cut out some things, but it's for the common good. And so we are in here, and that's, oops, that is this course here. And the red ink you see in those, the book excerpts that are in here are from the textbook, one of the sources for the class by Hennessy. And it's a standard, it's been updated over the years. And the president of Berkeley and the president of Stanford wrote it, and they're both tech people. And it's, the basic principles don't change over time. So it's a 2013 book. Now I'm recording this lecture in 2022, and I just played a recorded lecture from 2020. So I've been here in town for 23 years. It came in 1999. But this book is very popular. And what I've done in the red ink is updated the chapters. So you'll see in this lecture, not as much, but in other lectures where I've updated it. And so now we're down. So we just did this lecture here on the book chapter, the Hennessy book, and the high level language. And then I'll do this next one here. Go to the YouTube channel for that. It's already queued up because it's next sequentially in line in that stack, in that playlist on YouTube. This one's only 4 minutes, but this is really the most important thing for assembly language that I want you to know. Now, RISC versus CISC, I'd like you to just maybe, well, there'll be a review. I'll tell you what you need to know, but I want you to read every word of that textbook.
This very short one-page lecture is a continuation of some reading we just had where I mentioned some of this. And what I really want you to know from this is just assembly language is, and the 3 pluses, and then but is also in the three minuses, and then there are negatives. And then I'll just talk about some of the rest, but for this particular course, we're not learning to program an assembly language or developing an instruction set or anything like that, as we do in other courses. Just want to understand the main concept. So, high-level languages versus assembly language. So assembly language is faster, uses less memory, better control over hardware since it directly translates one-to-one to machine code. But it's machine dependent, right, for specific microprocessor or microcontroller. They each have their own instruction set. It's more difficult to program, need more lines of code, and you got to be very specific with your syntax. Even some assemblers, exactly where you put the code, exactly where that syntax goes. The code lines up in columns, matters. Difficult to maintain. Right? So those are 3 pluses and 3 minuses. Now, the rest here is just some enrichment you could think of. on different types of applications, and typically, high-speed embedded kinds of applications for assembly language, and then high-level language. So pretty much all applications, high-level applications. Oh yes, that says type of application, and then whether you use high-level language or assembly. I'll let you read through all that, but I would summarize without even looking at the table here that high-level language is for applications and for things where you need some complex coding. And assembly language is embedded systems where you need to be down near the hardware. You maybe need super fast speed. Maybe you don't even want an operating system. Good luck doing a high-level language without an operating system. Actually, I can think the case where you could, but assembly language, no. It's meant to be compact, fast. And then down below here, you see some examples of some high-level language, and then assembler, what that looks like. And this is just, somewhat obscure references for you. The MIPS processor, you probably won't see that nowadays so much. Was very popular for a while. And then Fortran, I mentioned, that's historic. And then C and Java, now we do see those. So, that translates down into some assembly language. And this is an understatement here that in 4 lines of code, you can do something that's in 3. I mean, you can have as many as 10, 20 lines of assembly language for one high-level language. I've seen that before. I've done that side of IBM. And then the machine language is simply ones and zeros, but there's a direct one-to-one mapping. You can't really see it here, but if you take my course 332, Digital Design 1, in there, we begin developing an instruction set and a computer and the hardware at a gate level design level. You design it. And so then that's where you learn that. And then you actually learn how to program an assembly language in a follow-up course after that, 333. And then there's also 433, Advanced Computer Engineering. We develop instruction sets in there too, but those are typically even more advanced for vector register kind of machines, or neural network processors, superscalar, multi-core, parallel pipeline, parallel processing machines. So first you got to get the fundamental. This is just an introduction here, basic introduction.
Okay. So again, the computer engineering courses, you hear me mentioning numbers there that are changing. In case you're watching these and you're in the transition into the college. These 2 courses, 332 and 333, are getting merged into here. And so the assembly language is getting packed in there into digital design as well as digital design. The interfacing is going to show up in the labs. And then there's other things that I'm pulling some out of, some talking about different kinds of AC motors and things that I lectured on it at IBM. Just drill down in there too much, but I'll just show you how there's a lot of stuff in here. So all the assembly language is getting packed into the new 330 course. Some of the simulation we talked about. This communication is getting bumped up to 433. Now it's going to be called 430, which is Advanced Computer Engineering, part of the parallel processing and interprocessor communication. The sensor fusion stuff, some of that's in the robotics class already. It's going to get ported into the new course. I won't do the AC motors stuff anymore. That was a Purdue lectures I did, but I'll put the DC motors in there. And some of this other stuff still needs to get up into those other courses too. So dealing with analogs and analog circuit stuff, relays and all that. More than you need to know in this course, but just FYI for anybody else in other courses, maybe listening to that. And so the new course will have all that stuff packed in there. And then 433 up here now is going to be called 430, which is going to be parallel processing. And you can see all that stuff got packed in up here as prereq. And then this is a lot of other stuff going on here in parallel processing. Supercomputer design. Okay. So I believe that may be good for this one lecture. Yes. Stop sharing here. Still recording. Does anybody want to say anything on the recording? I'll count to 5. If not, I'll turn off the recording and then you can ask questions not recorded if you like.